Hi everyone, welcome back. In this video, we'll be taking a look at one of the most important topics in Agentic AI and in NLP in general, which is vector databases. We'll be looking at some of the use cases in which you can use a vector DB, and we'll be highlighting some of the key decisions that you'd have to make if you were to use a vector DB in a production system. So the most common use cases for vector DBs are semantic search, recommendation engines, and RAGs. We will be covering RAG later in the certification, but for the purpose of this video, we want to show a real production system that was implemented at Ready Tensor that uses the first two use cases, semantic search and recommendations. So the first use case, semantic search. So imagine if a user is reading publications and they want to search for a specific topic. Semantic search basically is that you don't have to type exact keywords. You can search by whatever comes into your mind, and there should be an intelligent systems that decides which of these publications are the most relevant to the user's query. So that's the first use case. The second one is recommending publications. So whenever you're reading a publication, you should be getting some recommendations, things that are similar to the publication that you are currently reading based on the content of the publication itself. So whenever you're working on a project like this, the first thing that's going to come up is which database do I choose? And the possibilities are a lot. Here I included 5 of the most well-known options. And in order to choose one of them, you have to ask yourself some questions. Like, do I care about scalability? How much data am I going to have in the future? Is it storing data on disk or is it in memory? And how much does it cost? Things like this will determine your final selection. So at the end, we went with PgVector, which is an extension for Postgres. And let me discuss why did we eliminate the other 4. So for example, take Milvus. Milvus is excellent. It's highly scalable. The cost of it is higher than the other options, and basically it's built for handling hundreds of millions of vectors, which is not the scale we are going to work with yet. So we don't have to pay that much money for something we're not going to fully utilize at the moment. So you can eliminate the first option. If you look at FAISS, FAISS is basically, it's not scalable, but this is not the big problem. The bigger problem is FAISS stores data in RAM. It's not a persistent database, which makes it ideal for experimentation and learning purposes, but it's not going to work well in a production system unless you write custom code to persist data on disk, which is not ideal because you have other tools that can do this for you. But yeah, it doesn't cost much actually, or you might say it's free. So that's the pros of it, but we can't use it in a production system. Take Pinecone. So Pinecone again is really good, highly scalable, but it's fully managed, and yeah, we don't want to deal with other providers because we already have ours. So we preferred if we have an option which we can deploy ourselves. So that's why we didn't go with Pinecone. ChromaDB is really good. It was one of the options that we were going to pick, like we were comparing these two, ChromaDB and PgVector. And the only reason we picked PgVector over ChromaDB is that PgVector is a SQL database, like it's Postgres, but with an extension that allows it to store vectors. So you're basically working with SQL. Most developers are already familiar with how to query SQL databases. And both of them allows you to store metadata along with the vector, which is a requirement in our project because we needed to store the vectors about the publications, I mean the embeddings, and we need to store some metadata along with these vectors. So these two databases were good, but we picked PgVector mainly because it's easier to deal with, and yeah, basically it makes everyone's life easier. So after picking which DB you are going to work with, you'll find that there are other design choices that you'd have to make. For example, which embedding model do I go with? Do I use open source models, like the ones on Hugging Face, for example? Or do I go with OpenAI embeddings? So there are pros and cons for each option. So for example, OpenAI embeddings, they are very convenient because you don't have to worry about running the model. You don't have to worry about owning the GPU to run the model on. So these are good things about it. But on the other side, you have to deal with latency issues. So the last time I tried this, OpenAI embeddings used to take like 1.5 seconds. The API, I mean, it took like 1.5 seconds to return the results, which wasn't going to work well for us. So imagine that a user is typing in a search query and they have to wait for like 3 seconds before they get the results, and half of that time is going into OpenAI's returning the results. So yeah, that was one issue. And the other thing is, if you're going to use OpenAI embeddings, it means that you have to send your data over the network. And we didn't want to do this. We wanted to keep the data in our cloud. So that's why we went with the open source models, which fixes the latency and privacy issues. But on the other side, you have to run the model on your own. If you're using a GPU, you have to make sure either you own it or you get it from a cloud provider like AWS, for example. The second thing here is dimensionality. So what embedding dimension do I use? In our case, we use the MPNet base model on Hugging Face. It's a very popular model, very well known. And the embedding dimension here is 768. Now the question is, do I go lower than this or do I go higher than this, or is it enough? So generally, the embedding dimension shouldn't be too low to the extent that your application doesn't work well. And it shouldn't be too high to the extent that it takes much time to compute the embedding, because higher embedding dimensions mean you need more compute in order to do this fast. And you also have to make sure that whatever size you choose, that this model actually fits on your memory, like fits on your GPU, for example, because higher embedding dimensions generally means bigger models. So you would have to account for that. So the next key thing here is chunking. And why are we bringing up chunking in a VectorDB project? So remember, we want to embed our publication, meaning convert it into a vector, and we want to insert it into our VectorDB. And embedding models, just like any LLM or any transformer-based model, they have a context window limit, meaning you cannot pass infinite amount of text to these models. So if your publication is very long, you would have to chunk it, and you would have to pass each chunk on its own to get an embedding of this chunk. So after doing this, it means that you would have multiple embeddings for that publication because you converted it into multiple chunks. And what we do at the end is that we take these embeddings and we do a simple average, and we treat the output as the embedding of that entire publication. So that's why we are having chunking here, because we had to do it. And the question here is, which chunking method do I use? There are a lot of methods, not only these three that I mentioned here, but which one do we go for, or does it really matter? Because sometimes it won't matter. So in this particular case, it doesn't matter because we are not looking for a specific piece of information inside this chunk. It matters the most in RAG systems, so you would have to experiment with chunking. But for us, we are doing average anyway, and we want to end up with a single embedding for the publication. So really anything would work for us in this case. And we went for the recursive chunking. So the last key thing here is the similarity metric. So which one do we use? Do we use cosine similarity, or do we use Euclidean distance, or do we use something else? So from my experience, it's not going to matter that much. It's not like one of them makes the system works and the other one breaks it. But we went for cosine similarity for two reasons. The first thing is the MPNet model that we used, the embedding model, is actually trained using cosine similarity, which means it's expected to work well with cosine similarity over Euclidean distance. So that's one reason. And the second thing is the ranges of these functions. So cosine similarity ranges from -1 to 1, whereas Euclidean distance can be anything from 0 to infinity. So cosine similarity just feels easier to interpret in this case. So this is the high-level stack of this project. So we used Postgres, which is SQL database, plus the PgVector, which is an extension that allows it to store vectors. We used a Hugging Face model, and we used the EC2 service on AWS in order to run the server. So now let's take a look at a quick demo on the app to see how this actually works in production. So now I'm in the app. So let's show how these two use cases are actually working in production. So the first one is searching publications. So I'm going to use an example that's somewhat vague, meaning you don't know what you should expect from the system to return whenever you're typing this. So I'm going to go with something like, I'm very hungry. And let's see what we get. So you see the first 4 publications are all about food. In fact, a lot of these things are about food. Food Copilot, personalized nutrition, food recognition, and so on. So actually all of them are about food, even though I've never included the word food in my search query. And this tells you this is powered by embedding models and vector databases. This is not an exact search functionality. So this is the first use case, which is just searching. The other use case that we talked about is recommendation. So whenever I'm reading a publication, I should get similar publications to the one I'm currently reading. And for this, let me just go to one of our publications, which is this one. So this publication is about time series. And if you scroll to the end, you'll see that the system is suggesting other publications that you might be interested in, and all of them are also about time series. So here's time step classification, forecasting, stock market, stock prices, and yeah, this shows you how recommendation can be done using a vector database. So that's it for this video, and I'll see you soon. Take care.